Bismillahirrahmanirrahim. Assalamualaikum. We meet again for the third part in the lecture video frequency modulation. So today we will discuss about BESSEL function. This is the person who is named after the function, BESSEL function. His name is Frederick Bessel, born in 1784 in the present-day area of Germany. Bessel function from Wikipedia, defined by the mathematician Bernoulli and generalized by Bessel, the solution of the Bessel differential equation. So there are many applications of Bessel functions: electromagnetic wave, pressure, amplitude, heat conduction, modes, vibrations, diffusions problems, frequency dependent circular pipelines, dynamic floating bodies, and angular resolution, and so on and so forth. Because of this, a second order differential equation, there must be two linearly independent solutions. So Bessel function of the first kind, J alpha, solving this equation. So what is important from that is we have this chart, this graph, where we have the value of molecular index here, molecular index from 0 to, let's say, 10 or 12, and we have this, the value of Jn, the relative value of Jn. So we have J0, J1, J2, J3, J4, J5, J6, J7, J8, and so on. So from this figure, we can determine the relative amplitude of J when we are given the value of molecular index. So let's see one example. Let's say we have molecular index of 1. So here 1. So we will have the value of J0 is around 0.77 or 0.75, let's say, J0 here. And we have J1, we have the value of around 0.45, let's say here. So J1 is 0.45, let's say here, and J0 is 0.75 here, and we have also J2 is around 0.1 here, and the rest is not important. The rest of the J2, J3, J4 is not significant when molecular index is equal to 1. So that is the way we read this chart, this graph. Okay, that graph has been converted into the table known as table of Bessel function, where we have the molecular index and the value of J0, J1, J2, J3, J4 until J16 here. So how we going to read this table? Same as we read the graph just now. So we have the molecular index value here: 0, 0.25, 0.5, 1, 1.5, 2, 2.5, 3.3, 4, 5, 6, and so on and so forth. So when we have the value of molecular index, let's say 1, 1.0, so we have the J0 equal to 0.77. So J1 equal to 0.45. J2 equal to 0.11, and J3 equal to 0.02. So this is called the significant sideband. Significant sideband. What it means is that when the value of motion index change, so change the value of significant sideband. The higher the value of motion index, the more the number of significant sideband. So for example, if we have motion index equal to 1, we only have 1 carrier and 3 significant sideband. But if the motion index is 2, we have the carrier here and the significant sideband become 4. Okay, if we have the more higher motion index, let's say motion index equal to 10, so we have how many? 14 significant sideband when the motion index equal to 10. Okay, so when we're given the problems, we will calculate the motion index, and from that we can get the number of significant sideband from this BESSEL function. So this value is relative value. If you want to get the real amplitude of the sideband, we need to multiply this value with the amplitude of carrier signal. So this is the chart again. Okay, this is the motion index. Motion index is delta Fc over Fm. So note that for a low motion index, the amplitudes of the higher sidebands fall off rapidly. Okay, so for the higher sideband here, there is no significant at motion index equal to 1. Okay, so we can see here again, this is the carrier, this is not the sideband, this is the carrier, omega naught, omega naught or omega c, j naught, omega c. So this is the first sideband, second sideband, third sideband, fourth sideband, and so on. So first sideband is the frequency at Fc plus Fm and Fc minus Fm, whereas the second sideband, the frequency is at Fc plus 2 Fm and Fc minus 2 Fm. Okay, so from this chart, we can plot the frequency spectrum of Fm signal. Okay, percent modulation. Percent modulation is the ratio of the frequency deviation produced to the ratio of the frequency deviation to the maximum frequency deviation. This is called percent modulation. The ratio of the actual frequency deviation over maximum frequency deviation multiplied by 100. This is percent modulation. Next is the sidebands of FM. It is a product of any modulation. So any modulation we can produce, we can have sidebands. Angle modulation, FM and PM, will produce more bandwidth compared to amplitude modulation, AM. Bandwidth of FM signal is usually much wider than that of AM signal with the same modulating signal. Infinite number of pairs of upper and lower sideband will be generated. So we have discussed this before. This is the different feature of angle modulation. More sidebands means more immune to noise. So this is important to remember. So the more sideband the signal have, so it will become better because it is immune to noise. In most communication system using FM, maximum limits are put on both the frequency deviation and the modulating frequency. So this is the sidebands. So this is the first sideband, second sideband, and the number, and the last sideband with the n number of sideband. So this is the figure where we draw the sideband in terms of frequency domain. So we have the frequency and the amplitude. So this figure shows the sideband when the modulation index equal to 1, where we have here the amplitude of carrier is 0.7682 or 0.77 multiplied by Vc. This is the amplitude of the carrier. Next is the first sideband is 0.44 multiplied by amplitude of carrier Vc. So we get the real amplitude of the first sideband. The second sideband is 0.1144 multiplied by Vc. So this at the frequency, the carrier is at the Fc, and the first sideband is Fc plus Fm and Fc minus Fm, and second sideband is Fc plus 2 Fm and Fc minus 2 Fm, and so forth and so on. So this value we can get from the table, the BESSEL table. At modulation index equal to 1, we can have these values for the sideband, and these values for the carrier or J0. So we can say that from this, we can say that the bandwidth of significant spectrum is equal to 6 Fm. How? From here, 1, 2, 3, 4, 5, 6. So because at modulation index equal to 1, there are three significant sideband, J0, J1, J2, J3. So 3. So we have bandwidth 3 Fm at the above of Fc and another 3 below Fc. So altogether we have the bandwidth of 6 Fm. So this at the bottom here is the figure for modulation index equal to 5. So at modulation index equal to 5, we have 16 significant sideband or 8 pairs, and from that we can say that the bandwidth of signal Fm with modulation index equal to 5 is 16 Fm. Fm bandwidth. Theoretically, Fm signal contains an infinite number of side frequencies, so that the bandwidth required to transmit such signal is infinite. However, since the value of J and beta become negligible for sufficiently large n, the bandwidth of an angle modulated signal can be defined by considering only those terms that contain significant power or significant sideband. The actual number of sidebands depend on modulation index value. So we have seen in the table just now. So bandwidth, we can write the equation bandwidth equal to 2n Fm, where n is the number of significant sideband, those that have an amplitude greater than 1% in the BESSEL table. So we can see the BESSEL table, what is the value of significant sideband when we are given the value of modulation index. So we have discussed that before. So we can say that the bandwidth is equal to 2n Fm. So there is another way to determine the value of bandwidth, which is using Carsons Rule. The Carsons Rule gives the approximate number of sidebands depending on Carsons Rule by this equation, where the bandwidth is equivalent to 2 multiplied by delta F plus Fm. Carsons rule is an approximation and gives transmission bandwidth that are slightly narrower than the bandwidth determined using BESSEL table. There is slightly different in answer, but it is negligible. So we can use both BESSEL table and also Carsons rule to determine the bandwidth of FM signal. Power in FM. In FM, the amplitude of the modulated signal is the same as the amplitude of unmodulated carrier signal. Therefore, the power of FM wave dissipated in a loop is given by this equation: Pfm equal to V square RMS over R equal to Vc square over 2R. So this is the power. So Pfm equal to Pc. For the FM, average power is P total equal to Pc J0 square plus 2 sum of Jn square from n equal to 1 to n equal to n, where Pc is the carrier power, n is the number of pair of significant sidebands. The average power of the modulated carrier, Pt, must be equal to the average power of the unmodulated carrier. So that's all. Thank you very much for your attention. Okay, bye.